Hello everyone, and I took a little bit of a break, but while I wasn't uploading, I was solving more challenges, and I was recently able to do the calc challenge here on pwnable.tw after several weeks of trying. And it was a really fun challenge. It had a lot more reverse engineering than the other challenges. Like start an ORW, pretty much all you had to do was look at it. They were very small programs, so it wasn't very difficult to see what you had to do. With calc, it's actually a fully functioning calculator for the most part. Obviously, it has a bug and stuff like that, but it implements a neat algorithm that we'll check out and we'll see how to exploit. So really a lot more reverse engineering for this. So what we're going to do is we're going to go through kind of how I solved the challenge, how I kind of stepped through and understood the program. And then along the way, I'm going to try to explain basic concepts for in terms of assembly and stuff like that, just so that I know a lot of you wanted more 101 stuff. So I'll be trying to do some of that along the way. Next, I'm probably going to try to do hack note, because I've heard it's probably the next easiest one, judging by the solved numbers and stuff like that. You can see this one is only 155 despite being earlier than hack note, which is 775. So I'll probably try that one. But let's jump right into this. So the first thing to do is obviously to download the binary, which I've already done, and then run it and to see what it kind of does. So if we run the calculator, it says welcome to the secprog calculator, and you can input expressions and have it evaluate them. Oh, whoops. But you get the point. Can't do division by 0. So you can see it's like a real calculator. It can compute large values. So yeah, it does everything pretty much. So the first thing I would do is I would open this up with GDB Peta and check the protections on it. So GDB tac quiet calc, and then just run check security on it. You see you have a stack canary, we have no execute bit, and partial rel row. So a stack canary, in case you don't know, it comes from the concept of having a canary in a coal mine to notify you if the air down there is getting toxic or poisonous. So what a stack canary does is it sits here. I have a diagram here. It sits right before the stored base pointer and the return address, and if it's ever modified, then the program will exit with an error. So that way you can't smash the stack at all, because if you modify the cookie, then the program will exit and you can never overwrite the return address. So we have to bypass that somehow. And no execute bit, I'm sure you know what that is by now. Same with rel row, because we covered that stuff in my Raposaurus Rex video. So the next thing I would do is I would just kind of check out the control flow of the program, try to understand how it works a little better. And you kind of have two main tool options, in my opinion. You have Radare 2 and IDA. So I'll just show you Radare really quick, even though I didn't really use it for this. Oh, get out of here. So it's R2, binary name, analyze all this stuff right here, and then VV to see the visual mode, and then here you can see this is the main function. So we're just gonna set up a stack frame. It'll push the current value of the base pointer onto the stack, move the stack pointer to the location of the current base pointer, perform the AND bitwise operation on the stack pointer, which rounds its address to the nearest multiple of 16 to align it to a word boundary. make room for local variables by decrementing the stack pointer. Some weird comment. Sim.timeout is a timeout function that we'll look at later. Puts, welcome to the calculator, we saw that. And then it calls calc. And calc is going to be where we really start to analyze the program. So that's kind of the basics of Radare. If we go we can look at calc real quick, and you can actually see like control flow. You can move around. We'll look at this in IDA, but it's handy in Radare as well. You can see after every conditional, like this test here, which will do the end bitwise operator, and then the jump if the zero flag is set. If the zero flag is not set, so if the condition is true, then it'll follow the green line, and it'll do this. And if it's not satisfied, it'll follow the red line. And you just navigate it with the arrow pad. So that's kind of Radare's graph view. I didn't really use Radare though, because I think IDA is better, especially because of a feature we'll look at in a second, which is the pseudo code generator. So now let's head over to IDA and we'll really start to unpack the program. So it's a 32-bit binary. Load calc. And here we go. So let's look at the main function and then hit the space bar to look at the control flow diagram. Alright, so we're actually in the calc function, which is fine. But if we go to the main function, we see pretty much the same stuff as the Radare output. You can see the same calls, like all that stuff, but this time we're going to start looking at the actual assembly for the other functions, mainly calc. So there's a couple, if you look over here at the functions window, there's a couple functions we want to be concerned with. Get expression, eval, parse expression, calc. Those are the main ones. Everything else is pretty much irrelevant. So the main function calls calc, and the calc function, it looks like the first thing the calc function will call is b0, which will just zero out a certain number of bytes, set their value to 0. That's not important. Then it'll call get expression, and if we look at the assembly for get expression, it's going to call read, and this is these right here. It's trying to figure out what operation word that you've inputted, you know, like addition, subtraction, all that stuff. If we look at the regular assembly here, sorry, go back into calc, we can see, where is it? Here, the call to get expression, and then it does test EAX, because the return value of the subroutine get expression is stored in EAX, or in other words, your expression is stored in EAX. So it tests it, which does the AND bitwise operator, see if it's empty, and if it's not empty, if the zero flag is not set, then we jump to the non-empty expression, and the non-empty expression subroutine will do init pool, but we don't really need to be concerned with that. And then it'll call another subroutine parse expression. And one more thing, the test EAX, you may be thinking like, how can you do a conditional by doing an AND bitwise operator on the same data? Well, the AND bitwise operator just converts the data to binary and then multiplies them, which means that if there's any value other than 0, then you're going to have 1 times 1, which equals 1, and therefore you won't have the 0 flag set. But if you have just straight, if you didn't input anything, then EAX would be full of only have 0 in it, which means that when you multiply 0 by 0, you only get 0, and then you set the 0 flag, in which case you jump to the subroutine, which just exits the program. Sorry, I forgot to explain that. So, non-empty expression, I've what I've done is I've renamed this subroutine based off of the jump from from this line here. So when you're reverse engineering, you want to rename all the functions and the variables so that it makes the code easier to read. So I had to change all of these things. It wasn't like this when it came into IDA. They just had random variable names. So you always want to rename things, and to rename things, you really just double click. Oh wait, you just right click, rename, and then you can do it. Name it to whatever you want. Okay, so if you input in an expression, then it'll call parse expression. And this subroutine does a whitelist check. So let me just show you this cool feature. If you go to View, Open Subviews, Generate Pseudocode, we can see what IDA calls pseudocode of the disassembly, which is kind of like C code. And we can see what parse expression is doing. We can try and get a better sense. So this should be pretty obvious. It's preventing division by 0 by looping over your expression byte by byte. So it'll do that. Prevent division by 0. We saw that earlier. Then we have a switch statement here. And if you look at the cases, it looks kind of random, like Y45, Y37, Y42, Y47. But these aren't actually random. These are decimal representations of arithmetic operations. So 43 is addition. 45, I believe, is subtraction. 37 might be modulo, division, and multiplication. And the way to see these is to just look at the ASCII table. And 43 is addition, 45 is subtraction, 47 is division, and modulo is 37. So that matches up. And what you would do is you would like add comments so that you can remember things like that. So decimal for addition equals 43. And now you know whenever you see this that it's going to be addition. So this is kind of like a whitelist. It only allows certain operations to be performed, which makes sense. So the whitelist is basically just all your normal operations. And then based on what operation you input, it's going to call evaluate or eval. And eval will take your expression and an array to put the results in. And if you look at eval, it's literally just going to do, you can ignore this stuff for now, these comments. It's just going to check and see if the operator equals addition, if it's greater than addition, then if it equals subtraction, or if it equals division, and if it equals multiplication. And you can see these times equals there. And if you don't want to rely on the pseudocode, then you can look at eval here in the just raw assembly, and you see all these compare and jump statements. Compare will subtract the two values, and obviously if the two values are the same, then you're just going to get 0, because like 1 minus 1 is 0, 215 minus 215 is 0, which will set the 0 flag. So 2BH, let me just go to a hex to decimal converter. 2B, remember H is just the suffix for hexadecimal, is 43. So I'm going to add a comment. 2BH equals 43 addition. Yeah, here we go. So it's going to compare this value with the operation in EAX by subtracting them, and if then it's 0, then it's going to set the 0 flag, And if it is 0, then it'll jump to the subroutine, which I've labeled addition properly. And you can tell it's addition because of this. You can literally ignore all the assembly except for this one line here, add EAX to ECX, which you can assume would be the two operands of the whole expression. And if you look at the next subroutine, which I've already labeled as subtraction, you can see all the assembly is the same except for the one line that operates on the two registers that hold the operands. So in this case it's subtract, add. Same thing here, imul, and division. You can see idiv here. So once again, rename your subroutines, keep track of them, and yeah, just know how these instructions work in conditionals and various branches so that you can follow control flow. Okay, so the pseudocode will basically do all those operations and return the result. And yeah, that's pretty much it for the eval. We'll come back to eval later. And one thing I like to do when I'm do stuff like this is to actually draw out with pen and paper what's happening. So you can see I just use a clipboard and like regular notebook paper just to get a general sense of how the program works. So you can see I wrote get expression, jump equal, jump not equal, where does it jump, the whitelist, that as soon as I figured that out I wrote that down. Eval, checks of addition, multiplication. If it is yes, then it evaluates, no, blah blah blah. Then parse expression, I began writing that down. So this is generally a good idea because if you write stuff down, you actually remember it better. So thus you can remember how the program works better than if you were just staring at disassembly all day. So that's that. And now we have to get into the vulnerability. So the way to find a vulnerability with this program is really just to try out and see whether you can see what bugs exist in the program. So if division by 0 had existed, that might be a bug. But the other thing we can do is just run it and try weird expressions. So what happens if you, I don't know, do just +1? You only have one operand. You just get 1. What if you do plus 2000? You get a very weird value back, which, if you take this value, and it's always good to try this just in case, hex to ASCII. Oh, you can't read it, but I'll tell you, these are stack words. So, this is an arbitrary read with this malformed input, and we'll examine how that works in a second. What else? Let me think. Oh yeah, and I'll just show you. If I just leave this here, there is a 60-second timer for inactivity. Just understanding how the program works a little better. So 60-second timer. So moving on to how in the heck did our expression being plus 2000 lead to it spitting out random data we assume from the stack. And the answer to that lies in the eval function. So if we look back at parse expression, we see it calls eval with our expression as an argument. And if we go to eval, we see this here. So we inputted plus 2000, right? And our operation is addition. So we're going to satisfy this conditional. And now what it's going to do is it's going to take this array of, and this here is a pointer to the number of operands. So in a normal expression, 2000 plus 2000, there would be 2 operands because there's 2 things being operated on. But if we input plus 2000, there's only going to be 1. So this is 1, which means when it's dereferenced, 1 minus 1 is 0. So results 0 plus equals results 1, because this dereferences to 1. So you see we have control over the value of results 0. So normally where the result would go, we can put our input. And this is significant because if we go to the calc function, look at its pseudocode, it actually does, it prints, this whole line here is basically equivalent to printf res1. I don't know why this is here. That's mislabeled. So this prints result 0 because this is a counter of how many operands are in the expression. And if you're wondering how I know that's the counter of operands, well, it's the only thing that makes sense, because remember parse expression looped over the expression byte by byte to test whether it was an operation or an operand, and that it performs operations as it encounters them. We saw that. But this sub EEX1, it only makes sense to do sub or increment when you have some sort of counter. Like if you think of while loops, it'd be like while I is less than 0, I is less than 10, do stuff, and then it'll do I equals I plus 1, so it'll increment it by 1. This is kind of the same concept. You have a counter. So so it's basically just saying it keeps track of how many integers are in your expression, pretty much. And then it calls printf. But notably, what it does something weird with the input. It multiplies it by 4 and adds the number of bytes in an integer 4 to it. So it does a little math on our input before printing it to standard output. But that won't come into play until later. So let me look for my notes here. So we can actually talk about the vulnerability. Okay, so what did we already cover? We covered this. We covered this. Okay, so how can this arbitrary read be leveraged to remote code execution? So eval runs operations as they are encountered. So if we input plus 2000 plus 1, the program will basically run. Oh yeah, hang on one second. Before I get into this, I just wanted to say that what my explanations will be, like this right here, like you shouldn't take this as complete truth, like in 100% factually correct. This is just kind of my pseudo code trying to explain the concept. This might not exactly be what's happening, but it's kind of the result of what's happening, if that makes sense. So this is happening, but maybe not in the exact way that I'm portraying it. That goes for all my explanations, because I'm just trying to explain my thought process, which might not be entirely correct, but it still got me to the end point. So just a warning that not everything here will be technically correct just because it's pretty hard to be 100% accurate. So moving forward, if you do plus 2000 plus 1, then it'll basically do this operation because of the way eval works. And now we need to figure out how to control our input with this math statement here, this weird move statement, in order to print at locations that we want. So in order to really get arbitrary read, we need to be able to read values at a location of our choosing. And one of the main things we can do is we can try and read the value of the stack canary. And if you remember, we explained that the stack canary sits right below the stored base pointer and 4 bytes away from the return address. And the reason we want to read the stack canary is because if we can figure out the offset to the stack canary, then we also figure out the offset to the return address, because there's only a difference of 4 bytes. Because the word size on x86 IA32 is 4 bytes. So the distance between from here to here, 4 bytes. So if we can leak the cookies offset from the array, then we can leak the return address offset. So this picture is actually perfect because instead of having this char buff here for input, we have a buffer for our expression, which is 100 bytes. And if you're wondering how I knew it was 100 bytes, I know it's here. This was like, I renamed it obviously, but this was 100, and if you look at, let me go to parse expression. Here, S is your expression, and there's 100 bytes, so it's a 100 byte array. So basically this is the same thing. If we can figure out the offset from the array to the canary, then we should be good, and we can hopefully use math to write the canary to canary's value to standard output. And the way we're going to do this is we have to look at the subroutines again. So if we go to calc and look at the disassembly, then wait, let's go to I'll explain why this is the canary, but I know it is. So here, these would normally be different variable names. I've already renamed them when I was doing it, but you can tell what they are based on their offset. So 5A 0H hexadecimal. If we go to a hex calculator, 5A 0, just a minus 0. So that's 1440 in decimal. And then obviously these values are smaller than that because A is greater than 9 in hex, and then 5 is greater than 4, and then C is just 12. Which means that these offsets are relative to the base pointer. So if we look back at our stack, this is the base pointer, and if it's minus 12, then it's down 12 bytes. If it's minus 50 in hex, then it's down however many bytes that is. So this is what's called relative addressing. You can see examples of relative addressing all over the place. This is relative addressing, basically saying move 400 in hex into the location ESP plus 4, dereference that memory, and move 400 into that, 400 hex into that. And the relative addressing part is the plus 4 here. So it's saying relative to ESP plus 4. And it makes sense to do ESP plus 4, because if you look at the stack frame, the stack goes down from high to low memory addresses. So ESP plus 4, you're moving up the stack, where the program decremented the ESP to make room for local variables. So that makes perfect sense. So moving on, we have to look at this here. So we know 357 will be an EAX, or our number, so 2000 would be an EAX, but it's multiplied by 4, and then 4 is added to it. So in order to make our, so if we wanted to input 2000, then we would go to Google Calculator. So if you want 2000, then we have to reverse the operation. So 2000 divided by 4, and then plus 4. So if we wanted the program to print the value at the position of the offset of 2000, then we input plus 504, because when we do 504 times 4 plus 4. Wait, hang on a sec. When we do 500 times 4 plus 4, then we get the 2000. Am I just being dumb? I don't know, but you get the point. So, the cookie's offset is 12 from the base pointer. And since this is the furthest offset we have, 5A0, what we're going to use, we're going to go to our hex calculator. And we're going to calculate the offset, and we have 1428. So, relative to EBP, the furthest variable we have is 1440 bytes away. And then the difference between that variable and the cookie is 1428. So we go back to Google Calculator, and we do 1428. We divide this by 4, and then we add 4 to it, and we get 361. So 361 is the value we need, but we can print to get the return address because there's a 4-byte difference. But we can print the canary with the original 357. So might as well just demonstrate that now. And there we have what should be the canary. Not positive, but you get the point. So now that we have that, we need to look at how we can do an arbitrary write. So remember that the eval runs operations as they're encountered, so we can add values or subtract them or divide them or multiply them or perform modulo on any memory location with this. We already looked at all of this stuff, blah blah blah. And then obviously our ultimate goal is to exec v bin_sh. So now we can look at my exploit here. So I've included a bunch of possible gadgets, and the way you get the gadgets is you just go and then you do rop gadget just binary calc, and in a second it will return all the possible gadgets. And then what you want to do is, since when you do rop you normally want to just use pop, like that's the most basic, so I would just do like pop eax ret, pipe to grep. This is how you find actually useful gadgets instead of just a bunch of random stuff. And then you would take this, and this is a very good gadget, very simple. And then you would do it for the next register, so you do pop edx ret, because remember in eax we need to put 11 for the see there's another good gadget. EAX needs to have 11 for the syscall number. EDX and ECX need to have 0 for the arguments, and EBX needs a pointer to the file name, to the binary name, which is bin_sh, pointer to bin_sh. So that's how you get the gadgets. I did that in my other video as well. So you can see I have pop EAX, pop EBX. I have pop of all of 3 registers, separate one. So I just acquired a list of things. To make the actual syscall, we have a no operation, then syscall, or just raw syscall. Inc EAX can be helpful if you need to. You could theoretically do this 11 times in order to make EAX 11. You just chain it 11 times. Clear ECX and then push EAX for a possible null terminator. I wasn't really sure about that. But I'm not going to go through the exploit too much. If you know ROP, based on my other video, then it should be pretty straightforward. Basically all you need to do, the only twist here is that you need to write the difference between the address and the address of the gadget and the current location that you're on based on the counter. And the way to do that is you say, hey, take the difference between the address of the gadget and the return address and add the difference to the return address so that you're modifying the return address to be the address of the gadget. So that's all that does. And then here we pop 11 into EAX 00, and then BNSH null terminated into EBX, and then we do interactive. I'd say the ROP is the easy part, and the actual reverse engineering is the harder part. I tried a bunch of like exploit formats. Like here I tried clearing EAX, pushing null terminator, blah, 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 and then just doing the increment EAX 11 times. That didn't really work. So yeah, a lot of trial and error, but that's fine. No, that's the binary. Where was it? Calc 1. Alright, but anyway, moving on. So now we can actually, I'll just show the exploit. Oh, gotta call Python. Blah 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 blah, and there we go. Challenge finished. I'm not going to show the flag just because you can do it yourself, blah blah blah. But yeah, that's pretty much the challenge. I know it seems simple when I go through it, but this really took me forever, like forever. I needed some help to finishing it from a certain friend and blah blah blah. So it takes time. You have to be patient with reverse engineering. And another thing to remember is you only have to read assembly where it matters. So like you don't have to go to main and interpret what all this stuff is. You just need to say, oh, it's calling this subroutine, this subroutine, this subroutine, what's in here, blah, 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 and then keep going like we did. And the other thing I wanted to mention quickly is that it's kind of like a trap that I fell into when I was trying to learn reverse engineering. And that's a trap that thinking that looking at assembly, like here, I have a C program here that declares an integer to be 1, prints hello world, has a conditional, and if the conditional is satisfied, it prints yes. So I used to think I was like reverse engineering was just basically doing this. I would open up R2, I would do this, I would do this, I would do this, I would look at the disassembly, and I would be able to read it. I would say, oh wow, printf, and look, there's a hello world here, I wonder what it's doing. And then I would see this and I'd say, wow, I can read disassembly, wow, because look, printf and hello world, it's going to print hello world. And then what I would do is I would say, oh wow, look at this, there's a compare statement, and it's comparing 1 to a local variable, and previously it's moving 1 into the address of that local variable, so it's comparing 1 to the local variable, and then it's jumping, if they're not equal, to this subroutine down here, which just leaves and returns, and then if it is satisfied, then it's jumping here and it's calling printf again and it's printing yes. But the thing that you're missing here, if you think this is reverse engineering, or if you try to learn reverse engineering this way, is you're missing all the subtle intricacies of assembly that actually matter a lot. Like the fact that compare subtracts the two values, or the fact that call pushes the address of the next instruction on the stack, and then ret will pop it into EIP or RIP, and it'll go from there. Like you wouldn't be able to understand ROP if you didn't understand that concept of return-oriented programming. So, and like even setting up the stack frame, like lots of people, they do pwn challenges, but they don't know like what this stuff is for. So that's just like a kind of like a, I don't know, just a little piece of advice that you shouldn't really look for shortcuts, and looking at disassembly of small programs doesn't really make you a good reverse engineer. What actually matters is trying to understand the control flow, trying to understand how you can make the program act in ways it wasn't intended, and basically, not given a source code, try and piece it together in order so that you actually understand the program better than if you had the source code. Alright, so that's pretty much it. I hope you enjoyed. I'm going to get back to network security. I know I said that last video, but I will. I'm going to do Hacknote. I'm going to do another ROP challenge from Hack the Box. And then I have a cool tool that I'm working on in Python for network security that I'll hopefully be able to review. But until then, I'll see you guys next time. I hope you enjoyed the video, and yeah, just sorry if my explanations were a little rough. It's just because it's such a new, complex challenge for me that it was a little hard trying to put my thoughts onto paper and actually into words. So yeah, I'll see you next time.